Hello everyone and welcome to this virtual presentation. In this talk I will introduce you BlindOR, a new blind signature scheme from Lattice-Based OR proofs. This is a joint work with Patrick Harasser and Christian Janson. The talk consists of three parts. First, I will give you an introduction and an overview of our contributions. Afterwards, I will proceed to the main part explaining BlindOR. Then I will conclude. So let's start with the first part. So what are blind signature schemes? A blind signature scheme is an interactive protocol between two parties called signer and user. It allows a user to generate a blind signature on a message under the signer's secret key. The scheme is required to satisfy two security properties. The first one is called blindness, which means that the signer gets no information about the message during interaction. The second one is called one more unforgeability. It guarantees that the user cannot generate more blind signatures than requested. Blind signatures have different applications, most notably in anonymous credential systems. For example, blind signatures are used in the uProof technology designed by Microsoft. uProof is deployed in smart card devices produced by Gemalto, which is a leader digital security company. Other applications of blind signatures include anonymous eCash systems and e-voting. In an effort to develop practical blind signature schemes that are secure, or at least to be secure, against quantum computer attacks, various lattice-based candidates were introduced. The first one is by Ruckert at AsiaCrypt 2010. The scheme carries the core design of classical blind signature schemes over to the lattice setting. These classical schemes are based on the discrete logarithm problem and follow the Fiat-Shamir approach, which means it consists of three moves. The security proof of Ruckert's scheme adapts the one of Pointcheval and Stern, appeared at the Journal of Cryptology in 2000. Now, subsequent works given at Financial Crypto and ACISP last year introduced significant improvements, most notably removing the restarts induced by the user and reducing the number of rounds of the signing protocol from 4 to 3 moves. These schemes follow the same design principle of Ruckert's scheme and were shown to be practical. Then at Crypto last year, Haug et al. Pointed out a missing security argument in the security proof given by Ruckert. They introduced a new scheme following the same design principle but with a correct security proof. However, they stated that their solution is of theoretical interest only. So what about this missing security argument and its consequences? At a high level, the security reduction to the one more unforgeability property was incorrectly adapted by Ruckert to the lattice setting, and no sufficient arguments were made to ensure the success of the security reduction with high probability. Haug et al. Further also showed that further assumptions are required in order to obtain a correct security proof. Unfortunately, their solution entails huge parameters, which render the scheme impractical. This leaves us in a situation where current lattice-based candidates are either practical but not backed by a correct security proof, or impractical but provably secure. And this leads me to our contributions. We propose BlindOR, a new blind signature scheme based on lattices over modules. Our solution is simultaneously practical and provably secure. And the security of our solution is based on the hardness of two lattice problems in the module setting. The lattice problems are the learning with errors and the short integer solution problem, shortly MLWE and MSIS. The key technique used in BlindOR is the OR proof technique introduced by Cramer et al. At Crypto 94. Using OR proofs allows us to sidestep the missing security argument pointed out by Hauk et al. And the idea of using OR proofs is inspired by the work given by Abbo and Okamoto at Crypto 2000. And the table shown here gives a simple comparison between our solution and the solution given by Hauk et al. At Crypto last year. And this table shows that our solution significantly reduces the sizes of keys and signatures, as well as the communication complexity of the signing protocol. So now let me introduce you BlindOR. To this end, I will show you how the core design of blind signature schemes following the Fiat-Shamir approach works. For example, this is the framework of blind signature schemes based on the discrete logarithm problem and also based on lattice problems. The signer protocol is initiated by the signer, and it proceeds by computing a commitment to some randomness and sending this commitment to the user. Now the user blinds this commitment to obtain a blind one, and then evaluates a cryptographic hash function on input the blind commitment and the message being signed to obtain a challenge. Then he blinds this challenge to obtain another one and sends the result to the signer. Now the signer uses the randomness generated in the first stage and the secret key in order to compute a response and sends this response to the user. Finally, the user blinds this one to obtain a blind response and returns the message and its blind signature consisting of the blind challenge and the blind response. Now let me give you some observations on the previous framework. First, we know that the steps carried out by the signer are actually what a prover does in a Sigma protocol. Recall that a Sigma protocol is an interactive protocol between two parties called prover and verifier. It proves the position of a witness for some statement. In our case, in case of blind signatures, the witness is the secret key while the statement is the public key. And the protocol consists of three moves called commitment, challenge, and response, and the outcome of the protocol is a transcript including the commitment, challenge, and a related response. Now the signer corresponds to a prover in a Sigma protocol, and the user simply blinds this transcript to obtain a blind one. Now let me briefly show you how the security reduction to the one more unforgeability works. The key condition of the framework given previously in the previous slides is that there are multiple secret keys related to the public key. And in the lattice setting, the underlying lattice problem is usually the short integer solution or its ring variant. This problem is informally defined as follows. Given a matrix A, the goal is to find a short and non-zero vector x such that A times x is equal to 0. Now, given a matrix A, the security reduction, generates a key pair, a public key and secret key, and then runs the forger. Here we note that the forger cannot distinguish which secret key is used by the reduction, even if the forger knows all related secret keys. Now, when the forger returns an element Z, the reduction rewinds the forger to obtain another element, Z prime. Then the proof uses a subtle security argument to show that both elements Z and Z prime are distinct, so that the reduction returns Z minus Z prime as a non-zero solution to the underlying SIS problem. Now, Haug et al. At Crypto last year showed that the security argument given by Rickert is not sufficient to ensure that Z and Z prime are distinct with high probability. We solve this issue by using the OR proof technique due to Cramer et al. So recall that an OR proof is a sigma protocol obtained by combining several sigma protocols with each other. This protocol allows to prove knowledge of a witness for one out of many statements. The protocol has two crucial properties. The first one is the witness indistinguishability, which means that the protocol does not reveal for which statement the prover holds a witness. And the second property is called special honest verifier zero knowledge, meaning that there is a simulator that, given a challenge, it is able to compute a commitment and a related response, but without knowing a witness for the statement. And the simulated transcript is indistinguishable from a real one, which is generated by using a witness for the statement. Now, in BlindOR, in our case, we construct a lattice-based OR proof, which is obtained by combining a specified sigma protocol with itself. So that BlindOR works as follows. The public key consists of two statements, x0 and x1, and the secret key includes a witness for one of both statements. We call the statement with the witness a yes instance, which is an instance of the underlying lattice problem, and the second statement is called no instance, which does not have a witness. Now the signer simply computes two transcripts. The first one is generated using the witness, while the second one is generated by running the simulator of the underlying sigma protocol. And the key idea is to split the challenge generated by the user into two parts in order to create the respective transcripts. And the user simply blinds both transcripts to obtain blind ones and return the message and its blind signature, which consists of the blind challenge parts and the blind responses. Now the security reduction to the one more unforgeability works as follows. The input of the reduction is a statement, which is actually a no instance of the underlying lattice problem, and the goal is to find a witness for this statement. The reduction starts by generating another statement with a witness, which is actually the yes instance, and this allows the reduction to simulate the signing oracle for the forger. respond to signing queries made by the forger. Now then he runs the forger with the public key consisting of the yes instance and no instance. And in this case, the lattice problem underlying the public key must not admit multiple solutions anymore. And this is because that the OR proof forces the existence of more than one secret key. Therefore, and for the first time, we are able to use the MLWE problem instead of MSIS, which results in a much more efficient solution in comparison to previous works. And this is also similar to standard lattice-based signature schemes, which also use in the key generation the MLWE problem. And also the security reduction does not know a witness for its input for the no instance. And this is also analogous to the security proof of standard lattice-based signature schemes, and hence no further conditions are required to ensure the correctness and success of the security reduction with high probability. Now let me conclude this talk. In this work we introduced BlindOR. It's a new blind signature scheme from lattice-based OR proofs. Our solution offers practicality and at the same time provable security, assuming the hardness of lattice problems. In particular, the module version of the learning with errors and the module version of the short integer solution problem. Now, possible directions for future work are the following. First, to extend the work of Pointcheval to the lattice setting. This work is given at Eurocrypt 98, and it increases the number of blind signatures to a polynomial amount per public key, but at the cost of increasing the communication complexity of the signing protocol and also generating blind signatures in a sequential manner rather than in parallel. Another direction is so while our scheme is based on quantum hard assumptions, the security proof is given in the random oracle model, the classical random oracle model. So another direction is to prove the security in the quantum random oracle model in order to obtain a post-quantum security. A further direction is also to investigate new constructions of blind signatures from sequential OR proofs, which were introduced by Abba et al. At AsiaCrypt 2002. Sequential OR proofs were studied before and shown, for instance, by Fischlin et al. To provide ordinary signatures in the quorum. With this, I conclude my talk. Thank you very much for your kind attention.